Hello everyone, welcome to today's lesson. I am not there, I've got the bug, but you're there and you're ready to learn. I've had a shower and a wee nap and some vitamins, so I'm ready to go. And this is a review of free body diagrams and dynamics. And so here is our problem. It is a rocket, a 1,500 kilogram rocket. It is accelerating up into the air. That's a key word, accelerating. So it's accelerating up at a rate of 15 meters per second squared. There is a wind pushing it to the right with a force of 800 newtons, I hat, so that it moves to the right with a constant velocity. A constant velocity, that's important as well. 5 meters per second squared, I hat. Then it says draw a free body diagram and calculate all the forces, and that might be cut off, but anyways, that's the problem. So, free body diagram. Not all free body diagrams are going to have forces in all four directions, right? Sometimes they'll just have it in 2 or 3, maybe 1. With this one, we've got a couple forces. We've got a lift force shooting the rocket up. We've got gravity pulling it down. We've got a force to the right from the wind. And there's a force of friction. So even though there's the wind pushing it to the right, that might be that way, I don't know, pushing it to the right with wind, we know there's a force of friction as well, and I'll get back to that. So which one would be easiest to start with? The easiest one in the vertical plane anyways is going to be the force of gravity, and that is simply found through this formula. We know we can use the short one because this is basically on the Earth still. It's a little ways up, but it's not too high up. And we've been given its mass, and we know G is negative 9.81. And so the force of gravity, when we throw that in our calculators, negative 14,715 newtons. So we can put that into our free body diagram. So that's one done. How can we find F lift? It doesn't tell us the lift force that the rocket is giving, but it does tell us something else. It tells us that it is accelerating upwards. Okay, it's accelerating in the vertical plane, and this is positive, so it's accelerating upwards. If that's the case, these forces are not balanced. Okay, if there's an acceleration, these are not the same. Okay, and if it's accelerating upwards, that means that this one is bigger than that one. Okay, the lift force is bigger, and that's why it's accelerating upwards. Okay? Now, if we can find the net force upwards, okay, then we can find this one because we've got this one. Okay? Let's say that the net force is 120 newtons upwards. Okay? And let's say this is negative 20 newtons, okay, then the lift force is going to be 120 newtons greater than that one because the net force was 120 newtons. So this would be 140. Okay, so the net force is equal to the sum of these two. This one happens to be negative. And so I'll show you a formula, I'll remind you of a formula that we used for that. Okay, so first let's find the net force. We can use Newton's second law, which is F net equals ma. And we've got the mass, and we've got the acceleration. And so this formula that we derive from Newton's second law tells us that the net force is 22,500 newtons. Okay, so that means this one is 22,500 newtons greater than that one. Okay. So here's the formula that I was reminding you of. Okay, the net force is equal to the sum of these two forces. Okay. And so if we rearrange this for net force, or sorry, for the lift force, okay, and we can do that by subtracting the force of gravity from both sides, then the lift force is going to equal 22,500 minus the force of gravity. Okay, and so we have two negatives there. We end up adding them together, and the lift force is 37,215 newtons. Okay, so you're going to use this formula a lot. Okay, and sometimes it might be the force of gravity and the normal force, or other forces, but it's basically, and you're keeping in mind vectors, okay, which is directions. And directions include positives and negatives. Okay, so we've found the net force using F net equals ma. Once we had that, and because we had gravity, we could find the lift force. All right, we can throw that in. The easiest one in the horizontal plane is given to us. Okay, the force of the wind is 800 newtons in the positive I-hat direction, or to the right. Okay, so we can put that in. Now, what about the force of friction? It didn't even mention friction in the question. How did we know that there was a force of friction? Well, because the rocket is moving at a constant velocity. That means that the forces are balanced horizontally. This force is equal to that force. Okay? If there was no force of friction and just the force of the wind, it would be accelerating this way. Okay, but because these forces are balanced, it is moving at a constant velocity. It's not accelerating. It's all good. So the force of friction is equal, just in the opposite direction. Okay, so those are all of the forces. I hope that's a good review and that makes sense. You're going to work on a bunch of problems, and I think they're doable. So persevere, young physicists, and the answers are on there, so you should be okay. Okay.